All right, welcome everyone. Today we're diving into a really fascinating topic, the Epstein-Barr virus. It's a true master of persistence, and we're going to break it all down in this clinical briefing. So let's get started.
Okay, first things first, we have to talk about this number. Because honestly, it's just staggering. More than 90%, think about that, more than 90% of adults around the world are carrying this virus. So, this isn't some rare bug. For almost all of us, it's a lifelong passenger, just hanging out, completely asymptomatic.
And that right there, that sets up the big question for today, the central paradox we're going to unpack. How does a virus that's so common and totally silent in most people suddenly turn into a deadly pathogen? How does it go from being a harmless passenger to causing everything from mono to some really aggressive cancers?
So here's how we're going to tackle that. First, we'll look at its dual nature. Then, we'll get into the nuts and bolts, the viral blueprint and its life cycle. After that, we'll cover the whole spectrum of diseases it can cause. Then, and this is key, we'll zero in on the Dutch protocol for high-risk patients. And finally, we'll look ahead at what's next for prevention.
Okay, let's jump right into that first point, this idea of duality. See, in a healthy person, your immune system has the Epstein-Barr virus completely under control. It's an expert at it. But, and this is the crucial but, the moment that immune control slips, that's when the virus's pathogenic side gets unleashed.
Its formal name, of course, is human gammaherpesvirus 4, and really the key to its incredible success is its ability to establish a latent infection. Think of it like a delicate truce. The virus just hangs out quietly in our B cells, but it's constantly being watched by a vigilant patrol of our T cells. For most of our lives, this immunological standoff is the name of the game.
All right, now let's pop the hood and look at the fundamental virology here. If we really want to understand how this virus causes so much trouble, we have to understand the machine itself, right? Its classification, its structure, and its really, really clever life cycle.
Now, I know for this audience, the taxonomy is actually really important. Where the Epstein-Barr virus sits in the gammaherpesvirinae subfamily, well, that's not just a piece of trivia, right? This classification gives us huge clues about why it loves lymphocytes and its potential to cause cancer. It's what really sets it apart from the alpha and beta herpes viruses.
And here we have a great look at that classic herpes virus architecture. So right at the core, you've got the DNA genome, and it's protected by this tough icosahedral protein capsid. Then wrapped around that is something called the tegument. It's just packed with viral proteins, all ready to take over the host cell the second it gets inside. And then the whole package is wrapped in a lipid envelope. And this structure is exactly why it behaves the way it does in the lab. It doesn't cause those typical cytopathic effects you might expect. Instead, it immortalizes B lymphocytes. And that's a key reason why routine antiviral testing for it is so specialized and not really standardized.
So this brings us to latency. And really, latency is the virus's ultimate survival strategy. It's brilliant in a way. Instead of just replicating like crazy and getting wiped out by the immune system, it plays it smart. It circularizes its DNA, and then it just sits there, quietly, in the nucleus of our B cells as an episome. By turning off most of its genes, it basically goes into stealth mode. It becomes almost invisible to our immune system, and that's how it guarantees it can stick around for our entire lives.
And it's exactly this persistence, this lifelong presence that allows the virus to cause such a huge range of diseases. So what happens when that balance between the virus and us, the host, gets thrown off? Let's take a look at the clinical consequences.
What's so fascinating here is just how diverse the mechanisms are. Take infectious mononucleosis. That's not actually the virus causing direct damage. It's our own massive T-cell immune response to the virus, which is why we see it classically in teenagers. In little kids, the first infection is often totally asymptomatic. Then you have something like Burkitt's lymphoma, where the virus is a critical accomplice, you could say, to a catastrophic genetic event. And then there's PTLD, post-transplant lymphoproliferative disorder, which is a direct result of us. We medically suppress the immune system, we take off that T-cell brake, and the virus-infected B cells just start growing out of control.
But it's not just about cancer. The virus's reach seems to be expanding into this whole new, really challenging frontier, autoimmunity. And the link to multiple sclerosis in particular is getting so strong it's hard to ignore. It's really shifting how we think about what might be triggering these incredibly complex conditions. And now, we think we know how. We have a really plausible molecular mechanism. There's a viral protein called EBNA2, and it basically acts like a rogue master switch. It binds to our own DNA, but not just anywhere. It binds at the exact locations we already know are genetic risk spots for diseases like MS, lupus, and RA. And once it's there,
It hijacks our own cellular machinery, messes with gene expression, and could be the very thing that pushes someone who's already genetically susceptible right over the edge into full-blown autoimmune disease.
Okay, so the stakes are obviously really high. So how do we actually manage this risk, especially in our most vulnerable patients? Well, that brings us to the real heart of this briefing, the specific, proactive approach we use right here in the Netherlands to manage transplant recipients.
You know, the Dutch protocol is really elegant in its simplicity and how effective it is. The whole philosophy isn't about waiting for someone to get sick. It's all about preemption. It's about getting ahead of the problem. You identify who's at high risk, you monitor their viral load every single week using qPCR, and you act based on very specific data triggers. This is a bit different from some international guidelines that might also look for clinical signs. Here, the focus is really on stopping the disease before it even has a chance to start.
And here are the numbers. This is the critical data from the hematology.nl guideline. And these aren't just vague suggestions, right? They are crystal clear, actionable thresholds. If you get a single measurement of 10 to the 4th IUs per mil or higher, you start therapy, period. That usually means reducing immunosuppression and giving rituximab, and of course, you'd carefully adjust the dose for kids. It is a completely data-driven protocol that creates a direct line from the lab right to the clinic.
All right, so let's shift gears and look to the future. What are the challenges coming up on the horizon? We need to talk about antiviral resistance, and also, how do we handle prevention in our day-to-day healthcare settings?
So when we talk about resistance with Epstein-Barr virus, the #1 problem is what we call intrinsic resistance. Here's the thing. Standard antivirals like acyclovir, they only work when the virus is actively making copies of itself during the lytic phase. But most of the diseases we worry about, like the lymphomas, are driven by those sleeping, latent cells. So the drugs just have nothing to target. It's not that they don't work, their target just isn't there. Now, true acquired resistance, that's super rare, but when it does pop up, it works differently.
And here's a really essential point for a microbiologist to remember. Unlike with herpes simplex virus, this resistance has nothing to do with the thymidine kinase gene. Instead, if you see acquired resistance, the mutations are going to be in the BGLF4 gene that codes for the activating protein kinase, or in the BALF5 gene, which codes for the viral DNA polymerase itself. And finally, let's talk about prevention in the clinic. Look, because this virus is everywhere, and people can shed it without any symptoms, we don't have special isolation rules for patients with mono. Infection control really just boils down to the rigorous, consistent application of standard voorschapmaatregelen, our standard precautions, for absolutely every patient. And that especially means meticulous hand hygiene.
So let's end with a big question to think about. We've gotten really good at managing this virus in transplant patients, for sure. But with these deep connections to autoimmunity coming into focus, it really feels like we're just scratching the surface of what this lifelong viral passenger is truly capable of. Could the Epstein-Barr virus actually be the key that unlocks the mystery of some of our most challenging chronic diseases?
Just so you know, all the information for this clinical briefing was compiled using a Gemini deep search. And for anyone who wants to really dig into the data, we've put together a complete list of all the sources for you in the linked Notebook LM document.
And that's a wrap on this explainer. Thank you so much for tuning in. We really do create these briefings for professionals like you. So if you got something valuable out of this, please consider subscribing for more. And honestly, we would love to get your expert feedback down in the comments. Thanks again, and we'll see you for the next one.